So hey everyone, and welcome to another episode of our deep learning framework. So this is going to be a very important episode in which we're going to build our own AutoGrad. Remember previously what we have done actually was created our own defined arena memory allocator, and we've actually successfully grab these spaces from that huge arena for all the tensors and activation for forward and backward passes. In case you haven't watched the videos, go please check out the previous one. And we were successfully able to train our model, using our own custom defined memory allocator. So what it does is basically it defines the huge memory block. In C, it's always a linear block in one dimension. So, you just use different formulas to to transition from, single layer architecture to multiple dimensions. For example, in C, under the layer, underneath, what you do is you just define one huge block of array, and then you just create rows and columns and batch size and dimensions off of that, right, using some special formulas. So in case if you haven't watched these previous videos, go please check out those. Today what we're going to do is we're going to build our own AutoGrad. And what do I mean by AutoGrad? First of all, so AutoGrad is something that if you're coming from PyTorch or TensorFlow, you might have used this function called loss.backward, and this is the whole, you can say a brain of deep learning framework. So loss.backward is what happens is basically you run the forward pass. So after all the operations, after all the layer norms, multi-head attention, fully connected neural networks, you just find a one tensor, and that is a loss tensor basically, right? And this is the loss that you're going to grab and move all the way up, right, all the way to the start, taking the gradients and updating optimizers layer after layer using chain rule, right? And this is what we're going to build now. This is very important part of deep learning framework. In case if you're successfully able to do that, we can certainly stamp this as a deep learning framework, right? So fingers crossed to me. First of all, let me just explain you the intuition. What we're going to do is, so for example, I've pulled up a sketchpad over here. Okay, and let me give you an intuition. So what I'm going to do. So before building AutoGrad, it's very important that you should have an idea of graph data structure, right? I'm really sorry, I'm not using like uh, I'm just using a mouse over here, so I think you can actually have an idea what I'm writing. So graphs, in graph of the type DAG, which is called directed acyclic graph, and as the name is self-explanatory, you can understand. I'm sorry, this is G. All right, so this is G. Directed acyclic graph. So it's directed, for example, this is one node, this is the other node, this is another node, and let me just, do this. Okay, so this goes to this edge goes to this node. This also goes to this one, and this one is all going here. It also goes here, and this one also goes here and here. So this is our DAG. And you have seen this image before, didn't you? So this is called fully connected neural network. So the idea that I'm trying to give you is, almost every deep learning framework, like certainly you can call them, underneath there is some directed acyclic graph implementation. So somebody asked me the other day in the comment section that is programming is still helpful, or do we like learn to program in 2026? And the answer is yes, because you have to have a familiarity of data structures and algorithms in case if you want to go build your own one. So if you don't want to build your own one, you just want to be an application engineer, that's perfectly fine to not have a deep understanding of the data structures and algorithms. If you're someone who just copies 4 lines of scikit-learn or TensorFlow and just trains the model and happy, that's really great. You can do it. But if you want to dig deeper and want to create your own framework, then you must understand the data structures and algorithms, right? So coming back to our point, so we're going to implement DAG. So how DAG? Well, you can ask me how we're going to implement for AutoGrad DAG. So essentially, let's say for example we have tensor A, right, and this is tensor B, for example, and what we're going to do is actually we are going to sum them, right, and let's say let's say we have the outcome is let's say C, and there is another parameter called F, right, and what we're going to do is we're going to multiply this C and F to produce, let's say, D, and then we're going to apply function sum, let's say, over D to find the loss, right? So as you see it, it's basically a DAG. There's no cycle in here, and it's directed. So A and B goes to, we apply some addition operation to find T, and then F comes in, and we multiply both these to find D, and sum D to find loss, right? So we're actually building a computation graph. So this is what your AutoGrad does underneath. So what AutoGrad does is basically, um, it just creates a computational graph. It doesn't, sees the numbers. It basically sees the graph. So for our backward pass, it knows that, yeah, this particular tensor is coming from these two operations, and keeps track of every single thing, right? And what do I mean by keep track of things? So for example, let me pull up the terminal now. Here's my terminal, and if I go to over here, cd, let's say tensor, uh, cd get, where are we actually? So yeah, we're on the repo. So tensor.c. So right now, tensor randomize. Okay, so right now our function, let me show you with, using tensor create. This makes more sense. This was the function which we were previously using for our framework, tensor create. And okay, so this is the definition of our tensor. So what we're doing actually is, we're defining a tensor abstract, which is called tensor structure, and it has some parameters, right? And we're using that exact same tensor again and again for the abstraction purposes, to rewrite the code again, right? So this is actually the tensor create method. So it takes the dimension and takes the shape, and shape is a pointer of the arrays, and the first, well, not the first index. You can say the first index would be batch size or sequence length, depending on the embedding dimension. Dimension of the tensor. So it's if it's two-dimensional, obviously the first thing is going to be shape. You can say a number of rows and columns, and for a number of rows we call sequence length and embedding dimension, right? So yeah, so we allocate a tensor, right? And then what we do is we just use malloc to define its shape and stride. And stride is something that, I won't be covering in depth these concepts, but to give you an idea, that stride is how many memory locations you want to move to to grab the, let's say, the next row. For example, you have 16 cross 32 for a two-dimensional tensor, and if you moved 16 locations, 16 memory locations or 16 bytes, you will have the next row, and then if you move 16 more, you'll have the next row. So for columns, what you do is you just move 1 byte and find the next memory location. So that's why we've defined a create tensor with shape and stride, right? And as you can see, the last dimension of this stride is always going to be 1, because for embedding dimension, you just move only one memory location to find the next index inside the memory, right? So this was our previous tensor function, and how tensor was looking like previously was something like this. Tensor.h. So this is actually the definition of our previous tensor, right? It has shape, it has dimension, it has dimension, it has data. Now we need to modify these tensor. Modify this tensor for like AutoGrad. Let's call it AutoGrad, right? So what more parameters we need? What more parameters do we need? So we need to keep track of all the tensors and how they were built. So the first thing is going to be, I'm going to define a data structure called op, right? Or operations, and this is going to be called creator, right? And operations that created this tensor. So like I mentioned earlier, so in this case, this particular tensor was created by some operation, right? So it will be having a list of all the operations that basically created essentially this particular tensor. And there's going to be one more thing. I think you might have guessed that. We'll be having an array. Yeah, we'll be having an, let's say, let's say tensor parents. So this will be array of tensor pointers, right? And on each location, we'll be having a address to the all the parents, right? For example, let's say A was the parent and B is also the parent. So the array would look like something like this: so pointer to the A and pointer to the B, right? For this particular, for C, right? So we're having the addresses of the tensors that actually created that particular tensor, right? It could be more than two. For the sake of simplicity, I'm keeping only two parents here. Cool. And what else do we have? Operators, parents, and yeah, requires grid. Most important one, bool. You're familiar with this, right? Uh, requires grid, and this is going to be initially nothing. The third parameter is going to be requires grid, which will give us an idea that whether we need to update the weights of that tensor or not. So it requires grid or not, right? So yeah, these are the three parameters that we need to add in our tensor. And before we go into the full-fledged AutoGrad code, like I said, that we need to understand this DAG concept, right? And I just need to brush up on my graph concept. So I just created a file over here, which actually um, implements DAG for us first of all. So once I do that, it will be very important for us. It will be very easy for us to backtrack and find the tensors and upgrade their gradients while backward propagating, right? So if I talk about this particular thing, um, yeah, one more thing that I wanted to show you was, yeah, so you can ask me that how will we actually, how do we know that which operation comes first and then the next one and the next one? For example, if we move from loss to sum, yeah, we know that we need to apply sum is the sum operation, and then we find D, and then we have this multiplication, and let's say there's something some extra thing called G for the so this is RG, and let's say uh, this let's say this is some scalar multiplication with this thing, with the product of this, and then we find D. So are you understanding or not? So G is actually a scalar multiplication of some matrix with this product to find D. So how do we know that whether should we go for like this scalar multiplication operation first, or this product first? So this is where, when two operations are conflicting with one another, um, we use topological search, something called topological search, to find which operation, which gradients we need to update first, and then go for the next one, right? So we'll be looking into a lot of different details topological search later. So I just wanted to give you an idea that how we actually search through the graph while backward passing, and then update the parameters, right? So yeah, let me just quickly explain this DAG first, so it will help us understand in future in future how to build AutoGrad. So we defined a node, and node has data obviously, and node has the next node. So in case if I draw this DAG over here, so first of all, what we have is we have just a node, right? And it has some value inside, and then we have some next node to it, right? Very simple. Node architecture is very simple. Then we have something called graph, and it has number of nodes and adjacency list. So adjacency list keeps track of all the neighbors of one particular node, right? So graph will be having let's say a number of vertices. Let me just reload it. Okay, so number of nodes, right? And some matrix which which stores all the neighbors of all the you can say vertices. For example, A has neighbor B, and A also has neighbor C, and A also has neighbor D. So basically, at agencies list on first, you can say inside a list, agencies list, we have a array of linked lists, which basically store all the neighbors information of all the matrices, right? So for example, we have three nodes, A, B, and C. A has neighbor A, B, and C. So at this point, we will having a neighbor B, neighbor C, and neighbor D. And for B, we have neighbor, let's say C or P, and there's some P also here. And that's how I think you got an idea. So what it does basically, it's an array of linked lists, and each index stores a particular vertex neighbors in the form of addresses, right? Okay. Agencies list, and then we need to write a function that creates a node. So basically, just we're going to take data, and then we specify some space on heap, and then we populate this data, and then next node is always going to be none. And then we define a graph, and inside the graph we have nodes, and we define some graph space and define nodes. And agencies list, we define some allocated some space on heap for agencies list as well. So it's going to be nodes times size of node, because the number of the much as much nodes as we need, we just define its space on heap, and then we just use for loop to populate this agencies list. For now, it's going to be none, right? Okay, so now what we have done actually here is till here, till here, till here. Okay, so till here, we define separate nodes, right? In the form of graph. Wow. And now we need to add edges. So what we do actually is we add edge, we take graph, we take first parameter, first data, and second one. So we just create node B, and then we just assign in adjacency list, we just populate the adjacency list that B has neighbor A, right? And then we define this new node as a head node, because it should be at the start of list to if you just ever search it, we just find it off one time, right? So we define edges over here, right? And this is our graph. And now, very important thing. So you might have understood that what AutoGrad is basically, we just backtrack, right? And we just go node after node, and then we just know what the parents are, know what the operations are, and then we just see if requires grad is true. And if it is, what we do actually is just update the parameters, and we use topological search for that, which we'll discuss later. So this is actually, these three sentences were actually the recap of entire work, right? Now, the important part is we need to understand some traversal methods. So we know that there are two methods, breadth first search and depth first search. So for depth first search, what we do is actually we take node, we take visited list, right? And then we check that whether the node is visited or not. So if node is none, just return it. So otherwise, not otherwise, and also check that these are basically base cases of our DFS, right? So we check that whether this particular node is visited or not. If it's visited, then just break the loop, come out. And if not, then make this this node visited, right? And create a temporary node, right? And apply DFS recursively on that to keep on checking whether the node is visited. If it's not, go depth-wise and keep on checking. And if it is visited, break out of the loop, right? So we created our graph here, and we just created our visited list. For now, all of them are false. And then we check that if some particular node is not visited, then you apply DFS on it. And yeah, that's it. So this was actually the intuition of AutoGrad. I hope you might have gotten an idea of how things work underneath. In coming lectures, we'll be working on actual AutoGrad and see how everything works. And thank you so much for watching this video. And if you like my video, just give it a like, and I'll see you in the next video. Thanks.